Hi guys, today our topic is light, reflection and refraction. Before getting into the topic reflection and refraction, let us now see the basic topic, what is light. Light is a source of energy that makes us to see the things around us. Note that light is a source of energy that makes us to see the things around us. So here in this slide, there are two types, non-luminous and luminous. What are luminous objects? Luminous means the objects which emit their own light, are known as luminous objects. For example, stars. And the best example is our electric bulb, the bulb in our home. Then what are non-luminous objects? That's correct, they are the quite opposite things to luminous objects. So they don't emit their own light and take the light of the other things. For example, Earth. Earth takes the light of moon and sun. And the plants take the light of sun. So these are the examples for non-luminous objects. Now let us see what is a ray of light. The straight line of light is known as a ray of light. For example, this is a plane mirror. When you pass a light, this goes through a straight line, and this is known as ray of light. Let us see beam of light. Beam of light is of three types: converging, diverging and parallel. Is of three types: converging, diverging and parallel. Let us now see the example diagrams for them. Converging rays. So these rays, when a pass through a light, they get converted. When they are passed through a light, they get converted, meet at a point. This is the point. They meet at a point and get reflected back. Then what are diverging rays? They are diverted and do not meet at any point. They get diverted and do not meet at any point. Diverging rays, they get diverted and they do not meet at any point, such as this. So they don't have a point of incidence for them. Then what are parallel rays? If it is parallel, then these are known as parallel rays. Let's see these rays on a concave and a convex mirror. This is a concave mirror. When a light is passed on it, they get converted, and the concave lens have the converging rays. They get converted and got to meet at a point. Here, this beam of light is known as incident ray. And this is also called as an incident ray. Here, this is the reflected ray. And this is the point of incidence. Next, let's see it on a convex lens. If this is a convex lens, the convex lens have diverging rays. When you pass a light on it, they get diverged and they don't meet at any point. Here, this is the incident ray and this is the reflected. They don't have a point of incidence. The best example is a spoon. If this is a spoon, this is the concave mirror and this is the convex one. If you have take a spoon and try this activity at your home. Here this is the concave mirror and this is the convex mirror. Now let us see what we have revised till now. The thing, light. Light is a source of energy which enables us to see the things. Light is of two types, luminous objects and non-luminous objects. Luminous objects, the objects which emit their own light. Example, star and bulb. Non-luminous objects, which do not emit their own light and take the light of other objects. Here the examples are earth and plants. What is a ray of light? When you have a mirror, a beam of light is passed. This goes straight to the mirror. This is known as straight ray of light or ray of light. Then what is beam of light? Beam of light is of three types, converging, diverging and parallel. Here these rays are converged and they meet at a point, and this point is known as point of incidence. Here in diverging rays they get diverted and don't have a point of incidence. And these are parallel and they are straight always. Let's see these converging and diverging rays on concave and convex mirror. The concave mirror has converging rays and the convex mirror has diverging rays. When you pass a ray of light on a concave mirror, they get reflected back and meet at a point known as point of incidence. Here, when you pass a light on convex mirror, they get diverged and they don't meet at a point. Then they are known as diverging rays. So the best example in our house is the spoon. This is known as the concave and this is the convex. You can try this activity with the spoon at your home. Now let us see what is reflection. If there is change in direction of light or the light bounces back after reflecting on a surface, then it is known as reflection of light. For instance, let's define it. Light traveling from one object falls on another object and is reflected back. For example, the example is the ball. When a ball, if this is a wall and this is a ball, when the ball is thrown towards the wall, it gets reflected back like this. So the ball is the best example for reflection. And the another example is yourself. How can you see yourself in front of the mirror? That's right. When you stand in front of the mirror, this is a mirror. If you stand upon here, if you want to see the image of yours here, then there should be light. The light falls on you and it gets reflected back onto the mirror and directly reflected towards your eyes so that you can see the image formed on the mirror. This is the reflection of light. Now let us see the laws of reflection. First law, the angle of incidence is always equal to the angle of reflection. Let's take a bulb upon here. Here, the bulb emits light on its own, and let's take a surface here. When this bulb emits light on this, it hits the surface and it gets reflected back. Here, this is the incident ray, and this is the reflected ray. So, when the bulb emits light and it hits the surface, it gets reflected back. So, this is the point of incidence and these both are equal. If it is stretched back, for example, if it is stretched back, we take like this. It hits upon here and it gets reflected back like that. The angle is always same in the angle of incidence and equal to the angle of reflection. Now let us see the second law. The incident ray, the normal at the point of incidence, reflected ray always lie in the same plane. So these always lie in the same plane. When light falls on this surface, this is the bulb again, and when this bulb emits light on this floor, this gets reflected back. We know that. Here, this is the point of incidence, and the straight line towards it is known as the normal ray. Normal at the point of incidence. So here, if this surface or the floor is a example paper, so these all these three rays lie on the same plane, lie at the same point. This is the meaning of second law. Here, the angle of incident is always equal to the angle of reflection. Angle I, and this is angle R. We can write it as angle of incidence is equal to angle of reflection. There are two types of spherical mirrors. One is a concave mirror and another one is a convex mirror. How to see and where do you see them? The best example is a spoon. If this is a spoon, we have discussed this example at the starting of this video. We shall recollect it again here. If this is a spoon and this is curved inwards, and this is known as concave mirror, and this side is curved outwards, and this is known as convex mirrors. You may think, why we call these spherical mirrors if they are not in the shape of sphere? Because they are called spherical mirrors because they are a part of sphere. If, for example, if this is a sphere, this is outward facing and this is known as convex. And here, if this is the mirror, this is inner facing and this is known as concave. Here, they are a part of a sphere. You can see exactly here, they are a part of a sphere. Now let's see the points and the basic things in this sphere or spherical mirrors. Here, let us see the examples of concave and convex mirrors. Examples of concave mirrors: shaving mirror, torches, solar panels, etc. These are used because they are magnified. The image is magnified and it is shown larger than the plane mirror. Convex mirror: rear view and side view mirror in vehicles, because the image formed by the convex mirror is so small, so that we can see the vehicles around our vehicle, so in the small mirror, and it is clear. Now let's see the images formed by concave and convex mirror. The image formed by concave mirror is magnified and inverted. The image formed by convex mirror is magnified and inverted is the meaning that it is very large and it is upside down. An image formed by convex mirror is diminished and erect. Diminished means it is so small. In the convex mirror, the image is so small and it is erect. And it means erect means it is so still and calm. Next, let's see the important terms and the basic terms of spherical mirrors. Some of the terms are pole, focus or focal length, principal axis, radius of curvature, and aperture. Here, you can see the spherical mirror. This side is the concave mirror, as this is curved inside and these points are pointed to inside. This side is known as convex mirrors, as it is curved outside and the points are pointed towards outside. Here, for the concave mirror and convex mirror, the starting of reflection of light is known as pole. Here, this is known as pole. And for convex mirror, this is known as pole. Then, for concave mirror and convex mirror, this is known as curvature. As we saw here, center of curvature or radius of curvature. Let us mark it as R dot C. Next, principal axis. The common line passing through or the light ray passing through the mirror is known as the principal axis. For concave mirror, it passes from this side. The next one is radius of curvature, as we know that here, and aperture. Aperture means the place where the light is fall or the reflection of light is taken place. Here for concave mirror, this is the place where the reflection of light takes place. Let's mark it A. And for convex mirror, this is the place where the reflection of light takes place. And this is the aperture of convex mirrors. Now let us see mirror formula and magnification. What is mirror formula? Suppose let's take a concave mirror and an object placed at a certain distance from the mirror. The distance from the mirror and this concave mirror or convex mirror called as spherical mirrors is known as object distance, and it is denoted by letter U. When this object image falls on this spherical mirror, it gets inverted and the image falls down to the principal axis and it is inverted. The distance between this image and the spherical mirror is known as image distance. It is denoted by the letter V. And what is focal length? Focal length is that the distance between the pole and the radius curvature is half of it. Then it is known as focal length. Let us now see how we derive this formula. Here the focal length 1 by f is equal to the object distance 1 by u plus 1 by v, which is the image distance. You can use this formula to find any of things such as object distance or focal length or image distance. You may think, what is this formula? This formula is used to find focal length if only the radius of curvature is given. You can see in this principal axis that the radius of curvature and the focal length is half of the radius of curvature. So radius of curvature by 2 is known as focal length. For suppose, let's take radius of curvature value 10. F is equal to 10 by 2. Then focal length is equal to 5 centimeters. Now let us see what is magnification. Let us see what is magnification. Before getting into this, let's see some ray diagrams of concave and convex lenses. Let's see of concave lenses first. Here is the principal axis and this is the concave mirror. Here, if the image is enlarged, how it will be? Let's see. If we take the object here, if the image is enlarged, it will be back side of the object. Then it will be here. It is enlarged now. Let's see the ray diagram for this. Goes like this here and it comes here. From here it goes like this and it will come again to it. Here is how it flows. Here, this is the pole, this is the focal length, and this is the curvature. This is the first one. Let us see how it is when it is diminished. Let's again take a concave mirror, and this is the principal axis. This is the principal axis, then this is the object. For diminished image, the object will be forward or the image will be forward to the object. If it is diminished, it will be in this size. Let us see the ray diagram for this. From here to again to this point, from here again to this point. This is how the reflected ray goes, and this is the incident ray, this is reflected. Here again this is incident, this is reflected. Here this is the pole, this is the focal length, and this is the curvature. Let us see the concave lens when it is in the same size. The object and image are in the same size. It will be one down of another. Here is again a concave mirror, principal axis. Here is the image. If the size is same, here is the object. If the size is same, the image will be also just down to it. Let's see this ray diagram for this. Here is the incident ray and this is reflected ray. Here is the incident ray and again here is the reflected ray. incident ray, and here these both are reflected. Here this is the pole, this is the focal length, and this is the radius of curvature. These are the three diagrams for concave mirror. Let's see the diagram. There is only one single diagram for concave mirror. Let's see that. If this is the principal axis, let us now see for convex mirror. Here is the convex mirror, and this is the principal axis. If this is the object, then the image formed is so small and it is diminished. So the ray diagram will be now let's see our convex lenses. Here is a convex mirror. Sorry, it's convex mirror. Here is a convex mirror, and this is the principal axis. If this is the object, then the image formed is so small and it is diminished. And the second type is of the same size. If the image is formed near the mirror, the object is placed near the mirror, the image formed will be equal. So these both sizes are same in the convex mirror. Now let's get into the magnification. The ratio of height of image to height of object is known as, and this is used to find the amount of which object is magnified. So let's take it in chemical symbols. M is equal to Hi. Hi means height of image, and by HO means height of object, is equal to V by U. Here we can see the image distance is taken as Hi or height of image, and the object distance is taken as H or HO, which is height of object, which is equal to V by U. Here it is inverted, so this will be, here it is inverted, then it will be negative. If it is not inverted and it is erect, then it will be positive. Now let us learn about refraction of light. Till now we have learned about light and reflection. Here is about refraction. What is it? Refraction, the phenomenon of bending light when it is passed from one transparent medium to another transparent medium. Let's recollect it again. The phenomenon of bending of light as it passes from one transparent medium to another transparent medium. Let us see how with a picture here. If this is a medium, let us take, if this is a medium, then if you pass a beam of light like this, if it is reflected, it would go like this. But here it is reflected. Here it is refracted and it will go like this. It will be not parallel to the incident ray. It will be always opposite or slightly tended to other side from the incident ray. Here, the path of ray of light in the second medium is refracted ray. Here, this is the refracted ray. What is this? Here, this is the refracted ray. As common, this is the incident ray. But this is not the point of incidence. This is not the point of incidence. It is the point of separation. What is it? It is the point of separation. The angle between the refracted ray and the normal, the surface of separation, is the angle of reflection. Here they told, let's take this up. If this is the point of separation, then if this is the normal ray, they told that this angle, here I can see an angle now. This angle is called the angle of reflection. Sorry, it's a refraction. Here is the angle of refraction. Here you can see that when is the angle of incidence greater than refracted ray and the incident ray is lesser than refracted ray. Let's see how. Again, if this is the medium, if we pass a light beam of light here, if the ray is refracted such a way towards this, then this will be applied. That is, the incident ray is greater than the reflected ray. Here the incident is growing and it is going greater, but here the refracted ray is getting less. If you want the refractive ray more than the incident ray, then if this is the incident ray, then the refractive ray should be such as like this. Here this ray is refracted and it is more than the incident ray. Now let us see the examples of refraction. For first example, pencil immersed in the water in glass tumbler. When you immerse a pencil in the glass tumbler, it gets refracted. Let's see it virtually. Here is a glass of water and here is a pen. You can use a pen or a pencil, and here is a pen with me. If I drop this pen in this water, see what it happens. It is going to get magic. You can see here, this pen is so smaller and this is the incident ray. And here it is refracted. If the pen is in this ray and the refracted goes like this. This is the best example for refraction. And another example is prism. What is a prism? You will be knowing about the prism in the coming chapter known as the human eye. You would see the video of human eye in the further videos. How is a prism and how it will be? A prism is such like this. As I know, this is a prism. Don't think this is a four-sided triangle, but this is a prism. If this is a prism, if you shade it this part, it is a bit transparent. When you pass a beam of light like this, it would get refracted like this, but not straight through it. Like this, in any direction, but not straight to the incident ray or parallel to the incident ray. If it is going to the parallel to the incident ray, it would be like this. If this is the normal, if this is the normal, this is the incident ray, then the parallel refracted ray also would be like this. This is known as the parallel of incident and refracted ray. Now let us see activity. Now let us see an activity. Here you can see the activity, and it is done with a coin and bucket full of water. I don't have a bucket in this and for now, because I cannot show it to you in this video. That's why. Here is a coin, and if you drop the coin in the bucket such as this, it will go down. But you cannot take that coin in one shot, because the coin sees if it would be there, but the image of the coin is refracted there. If the image is like this, but if this is the refracted ray, the coin would be here, but you are seeing the refracted ray. So you cannot take it in one shot. You would move left, right, and sometimes you just. So this is an example for refracted ray and the activity. Next, let's get into the laws of refraction. Now let us see about laws of refraction. First law, incident ray, the refracted ray, the normal and the points of separation all lie in the same plane. See, if this is the medium or the plane, if this is the incident ray and this is the refracted ray, this is the point of separation, this is the normal. These all lie in the same plane. You can see this is plane, this is the plane, and these all lie in the same plane. This law is applicable for also the law of reflection. In that law of reflection, there will be a reflected ray in place of refracted ray. Okay, let's see the second law. Ratio of sine of angle of incidence. So so many offs. Ratio of sine of angle of incidence to the sine of angle of refraction is a constant for a light in a given color. If a light is given in a particular color, then the ratio of sine of angle of incidence, this is the ratio of sine of angle of incidence, then this is the ratio, then the sine angle incident and the sine angle refracted ray, they both are in the ratio, then this is the constant. Then this value is a constant. Constant means a fixed value, but the value is not known now. The refracted index. Let us see what is a refractive index. Refractive, here erect, refracted index of a medium for a light given of a wavelength. What is wavelength? Wavelength, it is measured in direction of wave. The direction of wave is known as the wavelength. In higher terms or in higher classes, it is defined as the distance between and current troughs, and the distance between current troughs and current crests, and this is applicable in the higher classes. Don't think this is there in the 10th class. If you want, you can take that, but it is a bit confusing definition. Next, speed of let's recollect it again. Refractive index of a medium for light in a given wavelength may be defined as the ratio of speed in vacuum to the speed of light in the medium. You may think, what is vacuum? Vacuum is nothing but an empty thing. Here, I have a box, but it is empty. If this is empty, this is known as vacuum because there is nothing in this empty space in the whole box or whole container. This is in the vacuum state. Let's get here. The formula is n is equal to speed of light in vacuum. You would be given in the topic coming up. Further in this video, you will be given vacuum of vacuum of some items or some mediums, vacuum of some mediums in the further video. This video, but after some time. N is equal to number, and this would be usually told as N21, N suffix 21. Suffix 21 is equal to speed of light in vacuum by speed of light in medium. If there is 0, let's think this is in a vacuum state, and take the value of 0, and the speed of light, let's take it as, you will know the speed of the many mediums in the coming video in this topic. You would be knowing that when we go on further in this video. 0 by 3.6 into 10 power 8 divided, no need, we can get the answer in 1 second. The answer is absolutely 0. Yes, it is absolutely 0, because 0 by 3.6, or if you take 0 by 1 CR, the answer is 0. No need to calculate that, but keep it in mind. If it is 1 CR, 1 crore by 0, then this is not defined till now in the history of maths or physics. Now, let us get into some mediums of refractive index and their values. Now, here are some refractive indexes of some materials for you. The refractive index of air is 1.03. The refractive index of ice is 1.31. Refractive index of water is 1.33. Refractive index of kerosene is 1.44. Diamond is 2.42. Rock salt means the salt which we get directly from the sea, 1.53, and alcohol 1.36. Finally glass, which is 1.5. And to find the refractive index, and it is denoted by letter mu. This looks like a letter U, but it is written like this. It is called mu. Now Here is a problem for you. The question is, light enters from air to glass having refractive index 1.5. Light enters from air to glass having refractive index of 1.5. What is speed of light in glass? They are asking what is speed of light in glass. And they gave that the speed of light in vacuum is 3 into 10 power 8 meters per second square inverse. Meters per second inverse. Now let us see how to do it. Now here n suffix g means the refractive index of glass is equal to speed of light in vacuum by speed of light in vacuum by speed of light in glass. So we need to find the speed of light in glass. If we both transpose the speed of light in glass and the refractive index, we will get speed of. So let us denote these letters with C by V. Let us denote with them. If we transpose V that side, we will get V is equal to C by mu. Here mu means refractive index. V is equal to C, 3 into 10 power 8 meters per second inverse by mu is 1.5. 1.5 cancels 3 2 times. So the speed of light in glass is 2 into 10 power 8 meters per second inverse. So this is how to find if they give a refractive index and if they give a speed of light in some object and ask you to find the speed of light in another medium. Now let us see the next topic. Now let us learn about refraction by spherical lenses. What is a lens first of all? A transparent material bound by two surfaces of which one or both surfaces are spherical forms a lens. It is telling that if a material is bound by two surfaces, if at least one should be a spherical mirror. If one or more also it is a spherical mirror, then it is known as lens. The definition is meaning. Then it also tells that this means that lens is bound by at least spherical mirror, as I told you, and the other is a plane. If it is bound by one spherical mirror, the other one is a plane mirror. Now there are two types of there are two types of lenses. One is convex lens and another one is concave lens. Convex lens means bulging outside, such as this. It will bulge out like this. And concave lens means curved inside, means it will be like this. Curved inside. And convex lens tells that it is thicker at the middle. You can see that here it is as thick it can be. And for concave lenses, it is thicker at the edges. You can see here it is as thicker as it could be at the edges. Now let us see the light traveling through these two lenses. Here you can see a convex lens. In this convex lens, when you pass a light, they get converged and meet at the point. As we know or we learnt at the starting of the chapter, converging lens. And this is known as diverging lens or concave lens. If we pass a light through this, it will get diverged. The image is not proper here, I will draw here again. If this is a concave mirror, when you pass a beam of light, they get diverged. They do not meet at any point. They are getting diverged. But in convex lens, they get, if a light beam is passed through it like this, then they both meet at the point. Now, let us see what is lens formula. There is nothing of lens formula. Lens formula is just opposite of mirror formula. The mirror formula is 1 by f is equal to 1 by v plus 1 by u. Then the length formula is 1 by f is equal to 1 by v minus 1 by u. Simple. Just opposite to mirror formula. Next, magnification. Magnification is just opposite to magnification of mirror. Yes, see. Here magnification is equal to height of object by height of image by height of object, which is equal to v by u. But in mirror, our image height of object would be minus v by u. In mirror formula it is minus v by u, and in lens formula it is just v by u, means it is positive. Next, let us see the final topic of this video, that is the power of lenses. And after we discuss the power of lenses, let's see two examples on lens formula and power of lenses. The degree of convergence of or divergence of light rays achieved by lens is expressed in terms of power. It is telling that the degree of converging or diverging rays achieved by a lens, the degree of which a lens is achieving converging or diverging rays is expressed in terms of power. Then what is power? Power is defined as the reciprocal of focal length. It is the reciprocal of focal length and it is denoted by letter P. The formula is P is equal to 1 by F. Power is equal to 1 by F. The SI unit of power is diopter. SI unit of power is diopter and it's denoted by letter D. If F is expressed in meters, then diopter is expressed in diopters. Means 1 diopter is equal to 1 meter. Just both are equal if 1 diopter is equal to 1 meter. The meaning is we have so many formulas for distance, meters per second inverse, like that. They don't have other units. Just 1 diopter is equal to 1 meter. This is the SI unit of power and focal length. Next, the power of convex lens is positive and the power of concave lens is negative. For example, plus 2.5 diopter of 0.5 meter is convex. How? Because it has a positive sign. Positive means convex lens. Minus 2.5 diopter of 0.4 meters. It is concave as it has minus symbol because concave lens is always negative of power. Now let's see the examples. Now let us see the examples on focal length, magnification and power. Now first let us see on focal length. Here the values of image distance is 10 centimeters, object distance is minus 15 centimeters, and focal length, we should find the focal length and magnification. So the formula is 1 by f is equal to 1 by v minus 1 by u. So the value of v is 10 centimeters and value of u is minus 15. So here minus and minus are cancelled. So it's positive, which is 1 by 10 plus 1 by 15 is equal to, the LCM of 10 and 15 is 30. 3 plus 2 is equal to 5 by 30, 1 by 6. 1 by f is equal to 1 by 6. So focal length is equal to 6 centimeters. If we transpose 6, if we cross multiply 6 into 1, f into 1, then we will get f is equal to 6 centimeters. Now let us see the magnification. M is equal to minus v by u. No, it's positive. As it is for length, it is positive. Plus v by u. The value of v is 10 centimeters. Is minus 15. The value of u is minus, so it's minus 10 by 15. So the magnification is equal to minus 2 by 3. Then the M is 0.66 bar. 6 is bar centimeter. So the magnification is 0.66 bar. Now let us see the problem on power. So here they are telling find the power of concave lens of focal length 2 meters. You may think it's simple, but you should always observe the lens here. For convex it is positive and for concave it is negative. So the formula is P is equal to 1 by F. Then minus T is equal to 1 by 2. P is equal to minus 1 by 2. Simple. So the power is 1 by 2. If it is for convex lens, then it is plus 1 by 2. Let's see some other example. If they ask here to find the focal length, here diopter, if they ask to find the focal length, if they give power is equal to 3D, find F. Then of convex. Convex means positive. P is equal to 1 by F. 3 is equal to 1 by F. Then 3F is equal to 1. F is equal to 1 by 3. If we substitute this, the value is F is 0.33 bar centimeters. That's all. If diopter, then the value is not in centimeters, it is in meters. So the value of F is 0.33 meters. So guys, this is the video on light. Let us meet in the next topic on physics or chemistry or maths. Till then, stay tuned to Steady Brains Academy and subscribe to our channel. Till then, bye bye and Jai Hind. But don't forget to answer the questions in the description box.